during the spring and fall. The appearance of the poles varies during the year from baked deserts to glaciers covered with solid CO2. Free water exists in the equatorial regions all year round. 2. Solar movement as seen from Uller. As seen from the North Pole, no sun is visible on January 1. On April 1, it bisects the horizon all day, swinging completely around. April 1 to July 1, it continues swinging around, gradually rising in the sky, the spiral converging to its center at the zenith, which it reaches July 1. From July 1 to October 1, the spiral starts again, spreading out from the center until on October 1 it bisects the horizon again. On October 1, night arrives to stay until April 1. At the equator, the sun is visible bisecting the southern horizon for all 26 hours of the day on January 1. From January 1 to April 1, the sun starts to dip below the horizon at night, to rise higher above it during the day. During all this time, it rises and sets at the same hours, but rises in the southeast and sets in the southwest. At noon it is higher each day in the southern sky until April 1, when it rises due east, passes through the zenith, and sets due west. From April 1 to July 1, its noon position drops down to the north until on July 1 it is visible all day, bisected by the northern horizon. 3. Chemistry and geology of Uller. Calcium and chlorine are rarer than on Earth. Sodium is somewhat commoner. As a result of the shortage of calcium, there is a higher ratio of silicates to carbonates than exists on Earth. The water is slightly alkaline and resembles a very dilute solution of sodium silicate, water glass. It would have a pH of 8.5 and taste slightly soapy. Also, when it dries out, it leaves a sticky and then a glassy, crackly film. Rocks look fairly Earth-like, but the absence or scarcity of anything like limestone is noticeable. Practically all the sedimentary rocks are of the sandstone type. All rivers are seasonal, running from the polar regions to the central seas in the spring only, or until the polar cap is completely dried out. 4. Animal life. As on Earth, life arose in the primitive waters, and with a carbon base, but because of the abundance of silicone, there was a strong tendency for the microscopic organisms to develop silicate exoskeletons, like diatoms. The present invertebrate animal life of the planet is of this type, and is confined to the equatorial seas. They run from amoeba-like objects to things like crayfish, with silicate skeletons. Later, some species of them started taking silicone into their soft tissues, and eventually their carbon chain compounds were converted to silicone-type chains, from diagram 1 to diagram 2, with organic radicals on the side links. These organisms were a transitional type, with silicone tissues and water body fluids, resembling the earthly amphibians, and are now practically extinct. There are a few species, something like segmented worms, still to be seen in the backwaters of the central seas. A further development occurred when the silicone chain animals began to get short chain silicones into their circulatory systems, held in solution by OH or NH2 groups on the ends and branches of the chains. The proportion of these compounds gradually increased until the water was a minor and then a missing constituent. The larger mobile species were then practically anhydrous. Their blood consists of short chain silicones with quartz reinforcing for the soft parts, and their armor, teeth, etc. of pure amorphous quartz, opal. Most of these parts are of the milky variety, variously tinted with metallic impurities, as are the varieties of sapphires. These pure silicone animals, due to their practical indestructibility, annihilated all but the smaller of the carbon animals, and drove the compromised types into odd corners as relics. They developed into a fish-like animal with a very large swim bladder to compensate for the rather higher density of the silicone tissues, and from these fish the land animals developed. Due to their high density and resulting high weight, they tend to be low on the ground, rather reptilian in look. 3 pairs of legs are usual in order to distribute the heavy load. There is no sharp dividing line between the quartz armor and the silicone tissue. One merges into the other. The dominant, pure silicone animals only could become mobile and venture far from the temperate equatorial regions of Uller, since they neither froze nor stiffened with cold, nor became incapacitated by heat. Note that all animal life is cold-blooded, with a negligible difference between body and ambient temperatures. Since the animals are silicones, they don't get sluggish like cold snakes. 5. Plant life. The plants are of the carbon metabolism, silicate shell type, like the primitive animals. They spread out from the equator as far as they could go before the baking polar summers killed them. They have normal seasonal growth in the temperate zones and remain dormant and frozen in the winter. At the poles there is no vegetation, not because of the cold winter, but because of the hot summer. The winter winds frequently blow over dead trees and roll them as far as the equatorial seas. Other dead vegetation, because of the highly silicious water, always gets petrified unless it is eaten first. What with the quartz speckled hides of the living vegetation and the solid quartz of the dead, a forest is spectacular. The silicone animals live on the plants. They chew them up, dehydrate them, and convert their silicious outer bark and carbonaceous interiors into silicones for themselves. When silicone tissue is metabolized, the carbon and hydrogen go to CO2 and H2O, which are breathed out, while the silicone goes into SiO2, which is deposited as more teeth and armor. Compare the terrestrial octopus, which makes armor plating out of calcium urate instead of excreting urea or uric acid. The animals can, of course, eat each other too, or make a meal of the small carbonaceous animals of the equatorial seas. Further note that the animals cannot digest plants when they are cold. They can eat them and store them, but the disposal of the solid water and CO2 is too difficult a problem. When they warm up, the water in the plants melts and can be disposed of, and things are simpler. Part II. The Fluorine Planet. 1. The Star and Planet. The planet named Niflheim is the 4th planet of Nu Puppis, right angle 6:36, declension -43:09, B8 type star, blue-white and hot, 148 light years distant from Earth, which will require a speed in excess of light to reach it. Niflheim is 462 million miles from its primary, a little less than the distance of Jupiter from our sun. It thus does not receive too great a total amount of energy, but what it does receive is of high potential, a large fraction of it being in the ultraviolet and higher frequencies. Watch out for really super special sunburn, and so on unwarned personnel. The gravity of Niflheim is approximately 1 g, the atmospheric pressure approximately 1 atmosphere, and the average ambient temperature about -60 degrees Celsius, -76 degrees Fahrenheit. 2. Atmosphere. The oxidizer in the atmosphere is free fluorine, F2, in a rather low concentration, about 4 or 5%. With it appears a mad collection of gases. There are a few inert diluents, such as N2, nitrogen, argon, helium, neon, and so on, but the major fraction consists of CF4, carbon tetrafluoride, BF3, boron trifluoride, SiF4, silicon tetrafluoride, PF5, phosphorus pentafluoride, SF6, sulfur hexafluoride.